Hi there, this is Math 148. This is section 9.2, looking at continuity and limits at infinity. So continuity is saying whether or not a function is continuous. And the book even says that this is a somewhat easy concept to grasp. I'm trying to find the page where it says this. It says, I'm reading on page 557, the graphs of continuous functions can be drawn without lifting the pencil from the paper, and the graphs of others may have holes. So basically, a function is continuous if you can draw it without lifting the paper, without lifting your pen, without lifting your pen. So that's kind of a nice, sounds like almost like an elementary school with pens definition, but here it is. Suppose we have a function like this. Whoa, so that one's continuous because I can draw it without lifting my pen. This one's continuous. Whoa. This one's continuous, right? So what's not continuous? Something that looks like this. That. Or how about this? Up, and then there's a hole, and you skip ahead. Or maybe one of those piecewise functions where it goes and then it hops and goes woo, like that. So this is the basic definition of continuity. Can you draw the function without lifting your pencil or pen from the paper? But now we have to be all mathy and fancy. So here's the math definition, just in case you thought we couldn't possibly confuse that issue. Definition says a function is continuous if, this is on page 557, if f of c, if that function at that value exists, and if the limit as x goes to that point, so the limit of the function as x goes to the point c, if that exists, remember there were some of them where the limit didn't exist, and if the limit as x goes to that point, c, of f of x equals the function at that point, f of c. So this is very mathy and a lot of notation, but let's do an example to show you in practice what this is talking about. So this is, actually I'll go back to white. This is question number 3 on section 9.2. I'm trying to find the page. It's page 564. Question number 3, page 564. And the question reads, determine whether each function is continuous or discontinuous at the given x value. Examine the 3 conditions in the definition of continuity. Well, isn't that fancy wording? So here's our function. F of x is equal to x squared minus 4 all divided by x minus 2. And we want to know, is that continuous at the point x equals negative 2? Okay, well, let's go through our checklist. Let's do 1. Does f of c exist? Notice in this case, that is c. We're talking about the point negative 2. So, what is f of negative 2? Well, that equals negative 2 squared minus 4, like this, times negative 2 minus 2. You see what I did there? Huh? Minus 4. And this is 4 minus 4. That equals 0. So the function equals 0, but it exists. So yes, it does exist. It just is equal to 0 at that point. So a situation where it wouldn't exist is if you had a square root of negative 4 or something like that, or 1 over 0. That would be bad. But this is okay. 0 over 4, that's 0. That's good. So check. 2, does the limit as x goes to, situation 2, we're looking at the limit as x goes to negative 2 of this function, does this exist? Divided by x minus 2. Haha, now we're back to section 9.1. So, remember what you can do is you can factor this if you like. That's x plus 2, x minus 2, all divided by x minus 2, right? Equals x plus 2. So we know this is equal to, you plug negative 2 in there, negative 2 plus 2 equals 0. So the limit again is 0, but it exists. So the answer is check. Let's write this. Equals 0. Check. Equals 0. Ah, you can see where this is coming. So does the limit of the function as x goes to c, does that equal f of c? Basically, are both of these pieces equal? Well, that is also true because we had 0 equals 0. So check. It's a lot of zeros, so that might be unsatisfying for you, but the answer is yes, this is continuous, and we have proven this algebraically. Notice this is at the point x equals 2. I'm going to show you on my graph. So here's the graph of the function. Do you see that? X squared minus 4 divided by x plus 2. If you look at the graph, it looks like a line. Why does it look like a line? Because when we simplified it, the graph looked like x plus 2. So that is why the graph looks like a line, because it is a line. Fancy, right? So what happens when x equals negative 2? Is it continuous at the point negative 2? Remember, we wanted the limit as x goes to negative 2. So when x goes to negative 2, yep, it just keeps going ding, 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 ding. It just kept on going through the station. Now, you might think, well, certainly it's not going to be continuous at the point 2. So what happens to 2 if I put my pen there? Come on, do it. Oh, here, I'll use my cursor. Might work there. 2. It was undefined before. There, 2, undefined. So if you were looking at the whether or not it was continuous at the point x equals 2, your answer would be no, it's undefined there. Okay, next problem that's covered in this section is limits at infinity. Limits at infinity. So it's essentially similar to what we were looking at with limits at a point. So what does a function do as x goes either to positive infinity or negative infinity? So let's look at question number 21 to illustrate some of the topics that come up with looking at limits over infinity. We have 8 over x plus 2, and the question says, for each problem, answer part A and B. So we want to use the graph. We're going to use the graph to answer these different parts. So part A has 4 parts. Don't you? My son hates it when math problems have more than one part per thing. So first of all, we're going to use the graph to find the vertical asymptote. Asymptote is a fancy math word. The line that it never reaches. So the graph, 8 over x plus 2. Here's the graph. So the vertical asymptote, is there a line here that it never reaches that's vertical? And again, vertical means going up and down. So yes, I graphed it for you. At x equals negative 2, you can see that the graph, as we zoom in, it approaches negative 2. There's negative 1, negative 2. See? Negative 2. It approaches that value, but it never gets there. So that is a vertical asymptote. Yes, at x equals negative 2. Part B, or part number 2 of A. It says find the limit as x goes to positive infinity of f of x. And again, you're supposed to use the graph. Let's look at the graph. Okay, so as x goes to positive infinity, we're going out. Okay, we're at 30. That's close to infinity. I'm joking. But you can see that x is going to 0. There is this line here that it seems to be approaching. And that is 0. As you go out in the positive infinity direction, x approaches 0. You can just see it on the graph. Part 3. What is the limit as x approaches negative infinity? You're saying, let's look at the graph going the other direction of f of x. This negative and positive is somewhat relevant. So we're going the other direction. So the graph x is going negative, 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 and it's still approaching 0. It's approaching it sort of from the negative side, but it's approaching 0. So do you see that? It's getting closer and closer to 0, and 0 is the line that it will never cross. So yes, it's approaching 0. And then part 4 says use this to define the horizontal asymptote. So the horizontal means going this direction, right? So in this case, oops, let's go back here to our paint picture. So the horizontal asymptote, you can see there's this line at x equals, y equals 0. I can write y equals 0 here. Y equals 0. That becomes the horizontal asymptote. The red line, which is our function, gets close to y equals 0, but it never crosses it. So the answer is yes, at y equals 0. Now we saw that from the graphing, but you can also tell this from the limit functions. If the limit of the function at positive infinity equals 0, and the limit at negative infinity equals 0, then that becomes a horizontal asymptote. Part B says check analytically. So this is what they mean when they say check analytically. Again, here's our function. F of x equals 8 divided by x plus 2. Leo doesn't like this function. A. So part A, we're looking for a vertical asymptote. Vertical asymptote. Well, they're saying, is there a place where this function is undefined? Yes, it's undefined when that equals 0. So if you had x plus 2 equals 0, it's going to be undefined at x equals negative 2. So that's one way you could find that, algebraically or analytically. Part B, or excuse me, this is technically like 1 and then 2. If we wanted to actually, without a graph, you just wanted to calculate the limit as x goes to positive infinity of 8 divided by x plus 2. Before we said that equals 0, but let's do it analytically. We're going to do this funky thing. So here's the funky thing. We multiply everything. You say, okay, there's an x here. When you have these infinities, you want to do the funky thing. The biggest power of x in this problem is x to the 1. So you divide, or you multiply everything by 1 over x. 1 over x times 1 over x. And this equals 8 over x divided by x over x plus 2 over x. Why on earth is she doing this? Wait for it, you guys. It's going to get amazing. So x goes to positive infinity. On top we have 8 over x. And on the bottom we have 1, because that turned into 1, plus 2 over x. Why do we do this? Because of a rule. It's the limit. If you have some number c divided by x, right? Maybe I shouldn't have used c, but that goes to 0. So that's handy. So what you're doing is whenever it's divided by x, you say that goes to 0, that goes to 0, that's 0 over 1. This is us doing the limit algebraically. 0 over 1 equals 0, which is the same thing we got looking at the graph. Went to 0. You think, why don't we just look at the graph? This is so much harder. And for doing the limit to negative infinity, you do the same thing. So it's basically 8 divided by x over x plus 2 divided by x. That all goes, when you infinity goes to 0, 0, and it gives you 0 divided by 1 equals 0. So that tells you when the limit equals 0, again, that tells you that that is a horizontal asymptote. I'm going to do another one for you with these horizontal asymptotes. They're a little bit tricky. Finding the limit as x goes to infinity of x cubed minus 1 divided by x plus 4, and this is question number 27. Again, I'm going to show you algebraically how to do that. You notice that x cubed is the biggest power. So what we do is we divide everything, or we times it all, by 1 over x cubed. You could either think of dividing everything by x cubed or multiplying it by 1 over x cubed. So divided by x cubed, divided by x cubed, divided by x cubed, divided by x cubed. So we're saying the limit of this function, I haven't changed anything because I've just multiplied the whole thing by 1 over x cubed, 1 over x cubed. See, this whole thing's actually 1. It's maintained the function. But now I'm saying this is the limit of x cubed over x cubed is 1 minus 1 over x cubed. This is just rewriting the function in a different form. X cubed over x cubed is 1 plus 4 over x cubed. Again, I've just rewritten the function. Why would I do that? Because now we can use this rule that 1 over the x goes to 0, 4 over x cubed goes to 0, and we get the answer is the limit as x goes to infinity of this function equals 1, because we had 1 divided by 1. So when you go through and you divide everything by x cubed, it helps you get rid of some of these terms. So we can see this on a graph. Do I have the right graph? I do! So here's the function x cubed minus 1 divided by x cubed plus 4, and we wanted the limit as x goes to positive infinity. So let's go to positive infinity, shall we? We're going to be here a while. I'm only at 45. I'm going for infinity. And you'll notice it's so close, this asymptote. I'll zoom in a little bit. But it's going towards 1. If we go back here, you think, what is that line it's going towards? You know, will it do this for me? It's going towards 1. It's the line of 1. See? It's going towards 1. It's getting close to 1. Do you see how it's getting close to 1? Oh, it's ever so close to 1. Come on. Anyway, so you can see on the graph that as x goes to infinity, the function is approaching 1. In this case, it's just saying, oh, forget it. I'm just going to call it 1. But it's actually approaching 1. It never quite reaches 1. So the answer, because this limit as x goes to infinity equals 1, means that there is a horizontal asymptote. Oh, it takes so long to write the word horizontal asymptote. At y equals 1. That was a check mark. Okay. One more. Hold on. Problem I wanted to do. It's question number 31. It's the same sort of thing, though. Find the limit as x goes to infinity. I think they always say positive infinity. Yep, because it could be negative or positive, of 3x squared plus 5x, all divided by 6x plus 1. So in order to find these limits algebraically, you can again think which of these x's has the highest power. Well, in this case it's x squared, so we're going to divide everything by x squared or multiply it by 1 over x squared, however you want to think of it. It's like this: divided by x squared, divided by x squared, divided by x squared, divided by x squared. Why do we do this? Because we want to let things cancel, essentially. Limit as x goes to positive infinity, that becomes 3, these x squareds cancel, plus 5, in this case there's 1x, that leaves the x on the bottom, 5 divided by x, that's all on top. And then on the bottom, 6 over x, 6 divided by x, plus, that's 1 over x squared. Okay, so how does this help? As the limit of x goes to infinity, this part goes to 0. Oh, that's 3, that's nice. That also goes to 0, and that goes to 0. So it sort of helped clarify that it doesn't exist. Essentially, we get 3 plus 0 divided by 0, and that's no good. That means no good. It means the limit does not exist. If you do this and you get 0 in the denominator, that means the limit does not exist, or you can write DNE. And that also tells you that there is no horizontal asymptote. And you can see this on the graph. I'll show you. So there's the function. Up here it's 3x squared plus 5x divided by 6x plus 1. Again, this is desmos.com. I'll send you the link. You guys can play around with it. So as x goes to infinity, what is the limit? Where is the asymptote? Is this function ever have a limit, or does it go off into space forever like Sandra Bullock in Gravity 12? The answer is yes, it goes off into infinity forever. It just goes up and up and up. So there's no limit on how big it gets. So the limit does not exist. So you wouldn't say the limit is infinity. You would say the limit does not exist. So limit does not exist. No horizontal asymptote. And you can see that again on the graph. There's no line that I can put in here. For example, you can't say x equals 10. Oops, sorry, y equals 10. Like it's going to cross any line that you put here, any horizontal asymptote, this function is going to cross it. So there's no horizontal asymptote. Okie dokie.